my name is Brien Porter. I'm with Intel Software. I'm part of the big data team within Intel Software. Just by raise of hands, how many people are from here in the Bay Area? Okay, how many are traveling today? Okay, good mix, about 50-50. Nice. So today we're going to talk about a new key value data store for heterogeneous storage architectures. So the agenda, we'll do a quick introduction. I'll tell you a little bit about the big data team within Intel Software. We'll go over kind of the background, our motivation, talk a little bit about the new hybrid layout key value data store. We'll talk about kind of the design, the implementation, go through some performance numbers that our team has run, and then we'll sum it up and kind of go over next steps. So the big data storage team within Intel is tasked to deliver optimized big data and open source solutions for Intel platforms. Spark, Hadoop, the ecosystem of that, as well as Ceph. We work closely with the community, with a number of committers within kind of each of the different products, along with our customers doing customer enablement and benchmark work. We deal with different types of new and innovative technologies, definitely into the real-time and in-memory and complex analytics, such as Spark, structured and unstructured data, things like Hadoop, agility, multi-tenancy, scalability, and elasticity around Ceph, and bridging advanced research with real-world applications and really trying to get it out and get it in front of our customer base. So in looking at this new key value store, really what we were trying to take a look at was where is storage hierarchy going to go tomorrow? You have at the top of this pyramid the CPU and RAM, which are small, the CPU cache and RAM, small, expensive memory. Down at the bottom, you've got our old friend hard disk and SSDs, which have really driven a lot of the new, more powerful applications with their speed and performance. To this, Intel brings 3D XPoint with currently our Optane storage platform, but also it brings into this realm persistent memory. So Optane up to 1,000 times faster than NAND, right? Giving you performance, giving you extremely low latency. So being able to bring that type of performance into the storage space and being able to leverage it as persistent memory, we're hoping can really enable newer cloud architectures. Along with the hardware, we also provided a number of new libraries that the engineering team has built. So, for example, the new NVMe libraries, PMEM.io, which are open source right now through GitHub, allow you to leverage the power of persistent memory by bypassing the kernel and from user space going directly to being able to allow your applications to directly access the persistent memory. Things like object, block, logs, these libraries have been put out there to make it easier for you to be able to develop against this new technology. So what is our motivation for looking at newer key value technology? One, to help with the overall adoption of 3D XPoint technology. Two, to start to extend newer software programming models, and as well as the fact that within Intel we really feel that persistent memory is going to be a really powerful driver for future storage media and to help the storage industry as a whole. We definitely feel that there are challenges in today's key value stores, particularly for cloud applications, and there's a need to both redesign the storage engine and rethink how best to leverage persistent memory for cloud storage. So the key value store engine model for the cloud, really kind of three major points. One, mission critical metastores for things like Ceph. Ceph is an open source software defined storage solution that works at scale. Our team works directly with both the Ceph and the Ceph committers and Red Hat and Inktank on Ceph development. Ceph provides object, block, and file store natively, and is the #1 block storage repository for open source. We have seen pretty significant adoption both in the kind of the tier 2 cloud providers, a number of large companies. We're starting to see more in the financial sector of different companies coming to both Intel and the community as a whole to do more to drive Ceph adoption. The second, a hybrid storage engine for something like hyper-converged infrastructures using different types of medium. Our team has been working on a technology, hyper-converged distributed cache solution that allows you to front end the key value store to allow you to leverage the key value store to do numerous different tasks in front of your choice of storage medium. And then finally, leveraging the new key value store as purely to drive large key value databases. So as an example, for a key value store engine for Metastore, Ceph's BlueStore. So Ceph, again, one of the most popular open source solutions for block storage in growing, leverages two different types of daemons. It's got its monitor that looks at the overall health of the environment, reliability, durability, and maintains cluster membership. But the OSD is what actually does the work against the disk. The BlueStore is the new backend for these OSDs, and has recently come out with the newer releases of Ceph. The BlueStore actually is what allows for the OSD to consume the raw block device. And if you look at kind of the picture that's there, you have a few monitors for a large series of OSDs that are maintaining the individual disks. Within that object store, BlueStore maintains writing directly to the data, and then it keeps a degree of metadata that it's running off of a small RocksDB. That RocksDB leverages a small file store, BlueFS. Now, we were originally using a Linux file system. They're now using an optimized BlueFS for writing directly to the disk. One of the challenges of using this key value store, however, is that whenever RocksDB goes to do its compaction, and it does periodically, you really get a level of stability, which really drains from the overall performance of the OSD. And what you basically have is you've got data trying to read and write to disk along with this file system that is also pulling from your metadata. The second example, the hyper-converged solution. So the hyper-converged distributed cache store allows for the caching of different types of APIs, block, object, file, to support different types of cloud backends, supporting Swift, Gluster, Ceph, and enabling some of the more advanced features around deduplication, compression, quality of service, and snapshots. This allows for a warm tier of data that's in your data center to be able to leverage things like cloud to store your data offsite on or offsite, and or to transit your data to an offsite location of your own. So the design goals of the hybrid data store, basically to keep this both simple and to keep it a general solution that can be used in a number of different ways. This was designed for the cloud, for high concurrency environments, to allow for a number of fixed length random read-write requests, and to be a high performance store that could leverage different types of media and really drive persistent memory. So on the left-hand side, what you see there is kind of a more typical way of writing to disk. Similar to the Ceph example I gave you, you have your data being written directly to the media, and on the right side, you've got your metadata going to a key value store. From the key value store, it still has to hit a file system before it hits your disk. And so you've got kind of two things contending for your disk I/O. On the right, you've got the hybrid data store. And what you're doing is you're sending both the data and metadata to the hybrid data store. It's leveraging the persistent media as a tier, and then writing the remaining data to the SSD without you having to deal with it. So take a look really quick at the architecture. So the architecture is in three different parts. The key value store engine allows for puts, gets, deletes, etc. You've got the RAM, which contains your key value store. You've got a read cache, write cache, and then a segment table. Persistent memory is just a tier, and it's written to first. And then you've got your SSD with a segment state table along with the rest of your data. So key is generated by an RMD 160 hash, creating your digest. The hash value contains both a pointer to your cache, if it's stored there, along with your data header and the physical address on the medium. With regard to the layout on disk, so your segments contain a segment header, timestamp, checksum, and the number of keys that are contained. The kind of key for this slide is really around the page-aligned storage. So it's writing as friendly as it can to the SSD medium so that it's writing as efficiently as possible. The segment state table is kept in RAM, but is also written to the SSDs for persistence. And the segment state table also contains the user state, free size, and death size. The death size cleaning out as garbage collection efforts. The write workflow, and basically your system is writing to the RAM immediately, buffering. Then it would get written to the persistent memory. From the persistent memory, the metadata would get updated in both the hash and the segment table, and cached on read, or cached for reads. Reading works very similarly. You're going to the key value store to get the information. It'll read from the read cache if it's available. If not, it'll either go to persistent memory or the SSDs and read as quickly as possible. One of the things to note is that because of the amount of information that's being held in the value store, it's able to, rather than doing an individual lookup and then having to come back, it's able to capture all of that data first, and rather than doing two reads to get information, one to get the location and then to go back and get the data, it's doing it all in one shot. Space recycling for the persistent memory is based on threshold, and as it reaches the threshold of space, which is tunable, particularly in the open source code that's out there, it will flush it to SSD and then update the metadata for the environment. One of the kind of clever things that the engineering team was able to do is they wanted to definitely make sure that segments that had the most amount of free space got prioritized to keep the reads as efficient as possible. If you notice the yellow segment, the second segment that's there, the system's going to prioritize that first as it goes to do its garbage collection. Place that one in first, then it would go to the first segment, and then it would go to the third segment, and as it goes through cleaning up, basically cleaning up the segments that have the most wasted space. And fast recovery. We all know that things happen, systems have issues. The hybrid key data store allows for contains a super block in the event that things don't shut down as we'd like. It writes to the hash table index periodically for each device, and the recovery will go through, read, and play that back.
Excuse me. I think one of the previous slides mentioned the iterator API. What can I iterate?
Let me take that question offline, and I'll get you the information. All right? All right. So the test that we've run against the environment. So this is the configuration of the test that we've run. And here's what we're seeing with regard to the overall write performance. So what we're seeing, particularly on latency, is a 1.5x improvement over RocksDB. By the same token, a 6x improvement, or over a 6x performance in IOPS. One thing you'll notice is that, particularly as the environment is spinning up, the performance isn't as good as, say, a RocksDB. What it's doing there is the system needs to have a certain amount of load before it's holding that before it does all of its writes. It's trying to do its writes in batches. Okay. With regard to reads, very similarly. With regard to read, you're seeing the same thing. Basically, as the system, as it hits about 32 threads, the system really begins to churn, and you really start seeing the difference between, say, RocksDB and the hybrid key value store, really allowing it to drive performance. And what you're seeing is up to a 4x, very close to the theoretical limits of the particular media. Wow. So kind of sped through that, I apologize. But the hybrid key data store really is designed to optimize hardware, to allow for a level of tiering, particularly for high-demand cloud workloads that demand kind of high throughput for fixed-length random read-write requests. It's leveraging DRAM, persistent memory, which will only grow in its footprints and its importance within the storage world, and then also SSDs. Our team is constantly doing evaluations around Ceph and BlueStore and helping to optimize that with the overall Ceph community. We are doing more and more evaluations around persistent memory and performance that you can gain out of that infrastructure. If any of you would like to take a look at it, we've got the website here on GitHub where you can get access to it. And thank you very much. Appreciate it.